In the previous video, we saw the forward algorithm for the hidden Markov model. And I'd like to, in this video, just take a moment to appreciate what happened here. What made this algorithm work, what made it dynamic programming, and why it's sort of so cool. So down here, we were analyzing the computational complexity of this model, or of this algorithm. And let me just make an aside here to make sure that you understand what I meant when I wrote this notation. So big O notation, I used big theta. Big O, if we say an algorithm is big O of some function f of n, that means that there exists some constant c and there exists some number n such that the time that the algorithm takes, I'll just write time subscript n, is less or equal to, or I guess I should say, exists n such that, maybe I'll put capital N here, such that for any little n greater than that capital N, the time that the algorithm takes on argument little n is bounded by the constant times f of n. So in some sense, the amount of time that the algorithm takes grows proportionally in some sense, or at least it's bounded by this thing which is proportional in f of n, at least when n is large. So that's big O of f of n. And if you have a function of two things, n and m, then you just have, it's the same, but then you have for all little n and little m greater than big N, that the time is bounded by that function. And here theta of f of n means, again, now there exist two constants, c and c prime, and there exists again a number, big N, such that for all n greater than big N, we have a lower bound and an upper bound. So c of fn is bounded below, or is a lower bound for the time that it takes, and c prime, maybe I'll put the prime here, c prime gives you a lower bound, and c times f of n is an upper bound. And actually, I guess here I need at least c prime to be strictly positive. Let me say c and c prime positive, and this one you could take to be positive also. It doesn't really matter in this case, but c positive. So the interpretation is that sort of asymptotically, when n is large, that the time of the algorithm, it grows with, it grows sort of roughly proportionally to f of n. So here, the time that the algorithm takes, the time that the forward algorithm takes, grows proportionally with this, n times m squared. And that's easy to see. Actually, in this case, it's directly, it's not even, asymptotically, it's actually directly. Well, and we of course, we talked about the reason why that is in the previous video, because you have, for each z, you have to do this computation, and there's m z's, and the computation involves m steps because the sum is over m. And we have to do it n times for each alpha, n times to get all the alphas. Okay, so why is this nice? So this is how much time the forward algorithm takes, and it turns out that the backward algorithm is also going to be linear in n rather. It's going to take basically the same amount of time. And let's compare this. So now let's see, why is this so cool? Let's compare this to a naive approach. Let's compare this. So the naive approach for the forward-backward algorithm, if you take on faith for now that we can do the backward algorithm in a similar amount of time, the naive approach to computing the same thing as the forward-backward, in the forward-backward algorithm altogether, we wanted to get the distribution, the conditional distribution on zk, given all the x's, right? And so let's just, this is just probability of zk and x divided by the probability of x. So under our assumptions, when we defined the model, the hidden Markov model, we know what the joint distribution is. So if we wanted to compute, let's say we wanted to compute this first one, probability of zk and x. Using the definition of the model, we would sum over a bunch of stuff and some, to marginalize out all the things that aren't in this expression from the joint distribution. So we would have to sum, I'll make a big sum because it's over a lot of things, over all the z's, all the z1, z2 up to zk minus 1, zk plus 1, up to zn of the joint distribution on all of them, x1 through n and z1 through n. And that would just be to compute the top. For the bottom, we would have to do it over all of them, so that's going to be roughly the same. This is over all z's from 1 to n. So let's think about this is going to be roughly the same time as this. It's just one less sum. So how much time would it take to do this, right? Well, we're summing over n variables. This is n nested sums, right? This would be like z1, z2, zn. And each of these sums is a sum over m things. M things in each of these sums. So it takes m to the n. There's m to the n terms in this sum. We're summing up m to the n things. So the time that this would take us to do is going to be like m to the n. So think about, for example, say m were like 10 and n were 100. If we had 10 states, z could take 10 possible values, and we had 100 points that we were considering. M to the n is 10 to the 100. It's an enormous number. It's huge. I mean, that's probably more than there are atoms in the universe. And this one was just n times m squared. So this approach would take at least 10 to the 100 versus the forward algorithm approach, or at least the forward backward algorithm approach, which was, what was it? I said n times m squared. So that would be 100 times n times m squared is 100 times 10 squared. So that's just, 100 squared. So that's not too bad, right? 10,000. Much, much better. I mean, this is trivial, especially compared to this. But this is not bad. 10,000 is very, very reasonable. So linear time, of course, linear time is going to be much better. But just to compare the magnitude of and then think about, if you were doing DNA or RNA or something where you have huge sequences, or even just language, the length of a document or something like that. It's just totally intractable. But this is not bad at all. So that was just to emphasize how, how cool it is, how much more efficient using the forward backward algorithm is than the naive approach. And what made this possible, right? How did we achieve this stunning reduction in the computation? Well, the basic idea is, it's the basic idea of dynamic programming. The basic idea of dynamic programming is that you're reusing things which you have already computed. So at least that's the way I think about dynamic programming. The way I think about dynamic programming, sometimes people abbreviate DP, dynamic programming, reuse earlier, if I can spell, computations. And if you think in terms of this principle, a huge number of algorithms can be interpreted as dynamic programming, as sort of dynamic programming and dynamic programming algorithms, and a huge number of problems can be solved efficiently using dynamic programming. Not everything, of course, but a very large number of problems can. And this is, I mean, this is a very sort of oversimplification, but if you had to reduce it down to, you know, to to 3 words, I guess, it's the basic idea is you're reusing earlier computations. And in the forward-backward algorithm, what the form that this took, the things that we were reusing were these alpha numbers, right? We set up this recursion, and we reused these alphas. So what we were reusing was the result of sort of, rather than recomputing these each time, this would have been like this. We could have also done just a big sum here instead of just summing over zk minus 1. We could have summed over all the z's from 1 to k for the, take the marginal distribution on z1 through zk and x1 through xk and sum out all the z's from 1 to k. And rather than doing that, what we were able to do was reuse. So we were able to reuse, the previous step and avoid summing all the z's from 1 to k minus 2, I guess. So that was the thing that we were reusing here, and that was what made this a dynamic programming procedure. Okay, so let's see. So next we're going to talk about the backward algorithm. But before we get to that, I wanted to just briefly mention, so I alluded to, or I sort of vaguely said that this is a very general purpose approach for Markov chains. And I want to explain that comment a little bit. So often, a lot of just sort of, if you take probability and you work with Markov chains, some of the basic problems that you have to do are things like computing hitting times, and if you have no idea what I'm talking about, then you could ignore this. But things like computing hitting times for a Markov chain, or expected number of visits to a particular state. And in general, a very, very general way to approach those problems is to set up a recursion. And that's exactly what we've done here. We've set up a recursion. So when you have to compute one of those, when you have to do one of those types of problems, the general approach is to set up a recursion for the thing that you're interested in finding. And then oftentimes, once you set up that recursion, well, if you're lucky, you can solve analytically for the result, for the thing that you wanted. Sometimes, you have to like invert a matrix or something like that. Or maybe you have to solve some recursion, and sometimes you can use generating functions to solve for the thing that the thing in the recursion. But this is the general thing that works so frequently in Markov chains. So okay, so I just wanted to explain that little comment. All right, so that's the forward-backward algorithm, and next up, we're going to do the backward algorithm, and then a little later, maybe we'll do the Viterbi algorithm for finding the maximum, the hidden states, the sequence of hidden states with the highest posterior probability. Okay, so next is backward algorithm.